I hope that there is someone who are familiar with this kind of a coordinate kind of a concept and system, but I don't think there is no volunteer to do the chapter 2, so I do the chapter 2. So I hope that I can explain clearly today, but I will try my best as I can. Okay. So today is the chapter 2 about the coordinate system. So actually in here, the authors actually explain a lot of concepts. And then, but the thing is, it's a kind of a very simple mathematical kind of a geometry kind of a concept. So it is pretty easy to understand actually. So I hope that it might be okay to explaining it. So, and then, oops, not this one. Okay. So everyone see my writing?
Yes, I can.
Okay. So everyone see the text, right? Do you want me to zoom in or I can do that? Yeah. Is that okay for you guys?
Yeah, it's better if you zoom in. Thank you.
Okay. All right. So let's start because in here actually there is a kind of a very good words kind of things in here because the data is not just a number and then it's a kind of a number within the context because this context is really matters because it's a context with the number. So in the 2.1 actually there is a first concept we have to understand is the quantity. Here is the quantity. Because in here it says about the quantity is the kind of a property of the some substances which is that has the magnitude, and then that can be expressed as a number and a reference. And then again, actually expanding to that kind of a concept of the quantity, it also explains about the reference is the measurement unit here, and then measurement procedures and or maybe reference material or combination of these kind of things. Actually, the concept of the reference is very important, and this one is what we really need to understand when we try to do the spatial data analysis, because reference is actually basically about the in here when you're looking down here is the base unit for the quantities or derived unit of the things, right? So when we scroll down a little bit here, so basically our SI system of the unit is the basic example, very simple example about the base unit like a length and mass and time, etc. And then there is also derived unit, derived unit like a density, or in here is like a kilogram per square mile, but in the maybe urban planning and social sciences, what we actually use is the population density, right? Because population density is the number of people per square meter, or maybe per square kilometer, or maybe in the US, maybe per square mile. That's the kind of a population density is the one we usually used a lot. And also there is a special case about the unit list measures that can lead us to the maybe unit is cancel out, like a mass fractions or maybe radian is the one of the typical example about the unit list measure. And another example is maybe when we try to calculate the G-score. G-score is actually does not have any units. So that actually allows us to the maybe we have a x1 and x2 calculated by the G-score. Even if this one is maybe populations, or this one is maybe income. Even if both unit are the difference, but the thing is, if we can standardize these two values with a G as a G-score, we can compare these two units together. Maybe if we really need to do that. But theoretically, G-score is a unit list measurement. So what is the a big advantage about the unit list measure is we can compare across the variable in terms of the value. Because G-score is really about when we try to do the normal standardized normal distribution. That G-score is just kind of a relative distance from the mean, which is right here, and then how far some specific value is from that origin, like a reference value. That is actually the basic concept of the G-score. So usually G-score is also another example for the unit list measure. So and then in here, for many quantities, later the origin actually value has a 0. So that means to make the quantities meaningful, that we have to define where is the 0 value, or where is what is called origin of that units. So it is very important to set up what the zero or origin of that unit will be. In case of the time and locations, we really need to be that kind of if we have a fixed origin locations or a fixed amount of the time quantity, and then based on that 0 kind of origin locations, we can actually measuring the differences, and also based on that 0 value, we can actually calculate the amount of the time as a durations. So that fixed origin is the concept is the datum. So that is a kind of absolutely position or location of the fixed origin is the kind of what is called the datum. And then let's go down a little bit. And then here is the so when we combine with those kind of a datum and measurement unit like a scale, that actually consists of the reference system. So reference system is one is the datum, and the other one is the like a measurement unit. So when we see about the ArcGIS, and then when we try to maybe for example when we in ArcGIS, when we open the shapefile, and then when we click that shapefile property, and then when we go to the source, we will actually easy to figure out what's the reference system in there. And then when you're looking closely in that sources property, you will find the datum and unit depending on the coordinate system we're going to use, which is going to be explained later in this section. So the second chapter is actually this book talk about what is called the ellipsoidal coordinate system. So in here is kind of this one is example of the ellipsoidal coordinates. So this is just kind of a matter of how we can. There is a point up here. It's a kind of a method of the representing the points. Okay, so ellipsoidal coordinate is kind of like there is two kind of representation of that locations. One is the polar coordinate, and the other is the Cartesian coordinate system. Because in here is the two-dimensional. Because this one is a y and this one is a x-axis, and then to represent the location of the point, we can thinking about okay, here is the x-axis is the 3, and then the y-axis is the 4, so that is the 3.4. In this way, we can actually think about the Cartesian coordinates. It's very simple, like just by using the distance from the origin, and then we can get identifying that point. The other way we can do is what's the angle of that point from the origin This is this one. And then the directly straight line distance from the origin. So that is the r and pi, right? So that way we can also represent this one. So both way will be represents the dead locations. So first one is we just only represent the dead points by using the distance, which is the Cartesian coordinates. Second one is the combination of the distance and angle. So that is a polar coordinate system. Okay. Any questions so far? Anything? Maybe I think I
One
can.
thing, oh, I'm
Yeah.
so sorry. One thing that
Uh,
I've never, I mean, that
uh,
I'm not 100% if I understand correctly, is that before when you said a reference system is, because I mean, I read the whole chapter, right? But a reference system is composed of a measurement unit and a datum, right?
uh-huh,
Or a
uh-huh.
datum.
Mm-hmm.
So when you say that measurement unit, does that mean if it's in lat long or in UTM, or does that mean meters, kilometers, and then the datum would be WGS 84, for example? So is that what it means by that reference system and that measurement unit?
Actually, theoretically, the kind of like when we say about the datum is a kind of like how we can define the origin is the kind of what is called the datum. So, like in case of the maybe state projection kind of stated plane projection system, that is kind of origin is kind of like just the centric of the Earth can be the fixed origin, or maybe we can define the somewhere like a Greenwich kind of location can be defined as a fixed origin. So depending about the how where we can define that origin, that actually constitute about the data. Okay. Because when we thinking about our Earth surface, we can actually define the somewhere, some location around the surfaces we can define as a origin, like equator or maybe north and south Arctic area. Depending on the where we can define the location, we can define those kind of things as a origin, as a datum, or maybe we can define our fixed origin inside the very centric point of that Earth sphere. What I mean? Do you want to mean? So depending on that kind of a location actually defines about what the WGS 84 is about, and then what the UTM is about. Okay, that's the kind of datum is about. And then reference system is we to have a reference system, we need that datum, which is the definition of the fixed origin, and the other one is what's the scale to measure the location, represents the location of each point across in the space. So those two components actually comprise reference system. Okay, how we can define the fixed origin, and then how you can measure the some distance or measure the locations of the some points. That's the kind of reference system is about, and then the datum is just kind of a matter of theoretically matter of the defining the origin. Okay. In
Okay,
this,
okay.
yeah, in this case, right? Okay, when you're looking at this picture, like a circle one, in this case, the fixed origin is just kind of in here, center, right? And then radius is 5, right? Maybe if we can define the origin like up here, like here, like y equal 5, and then this location point gonna be measured differently, like a straight distance from this one, and then maybe some of the angle for this, right? Like this. That's the how datum is about. Okay. Does it understand? Do you understand what I mean?
Yeah, yeah.
Yeah. Okay. So, and also in here is it's a kind of a little bit tricky, but why they use the arctangent? But arctangent is a kind of like inverse function of the tangent, like a tangent 53 in this case, because it's a 53-degree. Because some kind of a little geometry is the tangent and arctangent is kind of like an inverse function of those two. So we can also say about arctangent, or we can also writing about the tangent like this. Okay, and then this one is just kind of a matter of the ratio of the distance, but this one is actually give us about the if tangent value has this one, what's the degree of the that one to get that kind of value. So for example, like in here, in this case, when we have this kind of a square, not a triangle, and then this is a 45, and this one is a 45. In for example, that means this one is a 1, and this one is a 1, and this might be Pythagoras theorem going to be √2. So in here is a tangent 45, degree is 1, right? This is the tangent, right? T. And then arctangent 1 is actually 45 degree. That's the relationship between the tangent and arctangent. So actually arctangent is a kind of a try to represent about the degrees. So that's the kind of what this one is about. But anyway, so that is not that important. But and then here actually in this case we actually have this one is a 2-dimension, right? But now maybe let's talk about our actual real world cases, which is the 3-dimensional kind of Earth surfaces. So in that case, in the picture on the left is what we can do is about the Cartesian geocentric coordinate kind of system, because to identifying this point is here, we can say about from the here is the origin, which is the datum point, and then this one is X, and this is the Y, and then up to the top is the Z. So it is X point, Y point, Z is how we can represent the point. Just only using the distance from the point, distance from the origin, right? And then the other way we can thinking about is combination of the angle, 2 angles, and then radius of that sphere from the origin. So in this case, to represent this point from the origins, we have a lambda degree. After that, we have another pi degree, and then r. That is how we can represent these locations when assuming that these sphere kind of systems. So that's how we can represent. It's the same thing, just only matter of the adding the another parameters into the system when we have a three-dimensional kind of a space. Okay. And then, but what is the interesting about this is when we thinking about our actual Earth surface, actually Earth surface is not a perfect sphere, like a perfect circle, you know, because our equator, radius of the equator is slightly longer than this one, right? So in this case, we actually have two different kind of angles in here. So this one is just kind of a angle from the origin. And then the other one is when we try to do the tangent line, just try to passing through that point. And then this angle is a kind of like a location of the angle for this perpendicular kind of a relation, perpendicular kind of a line. Because the reason why the difference in these two angles is because of we have a eclipse kind of a shape in the Earth surface. But the thing is, assuming that we have maybe if we have a very perfect circle like this, and then there is a like this. Okay, this is the y, this is the x, and then assuming that we can represent this point like this. Maybe if we have a very perfect circle or sphere like this, when we draw the tangent line to passing through this point, this one is always perpendicular. Okay, from when we draw the straight line to that point and to that tangent line, it is always perpendicular to these two lines. That means these two angles gonna be the same. There's no difference. But the reason why we have this kind of angle differences is a kind of our Earth surface is not perfectly circle. If we have a perfect circle, it is always perpendicular to this tangent line and then this line. In that case, this one and this one actually the same. So there is no difference. But due to these kind of eclipse situations, we have this kind of a different angle. So that angle actually should be defined the geodetic and then geocentric kind of latitude. Geocentric latitude is from the angle measured by the line from the origin, and then geodetic angle latitude is the angle measured by the point with the tangent line, which is the perpendicular tangent line kind of a situations. So that's how geodetic and geocentric latitude is about. Okay. And then next one is just kind of we also in here is explain about the projective coordinates, and then just kind of a measurement about how we can measure between those two in here. So okay, how okay why okay. So in here, actually, when we try to measuring the distance, there is a two-way to measuring it. One is kind of like a distance about the Euclidean distance, you know, which is the Dij is just kind of a difference square difference between the two x-axis location and then the y-axis, and then we can square them and then root them, sum it and then root them. It is also the same thing even if we have a 3 dimensions. It's just kind of a matter of adding the g I minus gj and then square it and then sum all together and then square it. That is just kind of a very simple way to representing the distance between the 2 points. And then this Euclidean distance is it's just kind of a straight line distance of the over two between the 2 points. What I that's what I try to say. And then also maybe 2 point of circle kind of things. We can also thinking about the difference between the two angle and then multiply by the that distance from the origin can be measured by the that rounding that distance from the that arc of the 2 points. Like this one is just kind of a formula about the length of the arc. Like when we using the two angles differences, and then the distance from the from the origins. So that's another way we can also calculate about the distance. So any questions so far? Anything? Okay, I'm gonna move on then. So and then 2.3 is also talking about the coordinate reference system in here. So in here, when defining the depth to the coordinate system is a kind of like a mathematical rules to specifying the how coordinate can be assigned to the each point. So that means how we can represent the point location of the point. That's the kind of a coordinate system is about. Data means I already talked about the define the position of the origin and scale. And then a geodetic origin is describing the relationships about the coordinate system to the Earth. Okay. And then coordinate reference system is the datum and then a scale of the unit, like a measurement unit, can be compromise a geographic reference system. And then in here is just about talking about the topology of the Earth, because we actually know about the Earth is not exactly the perfect sphere. It's like a ellipsoid kind of things, and at the same time, when we try to looking at this kind of surface, this kind of surface is not the flat like this kind of a line. It always have this kind of a like ups and down due to the elevation of the points. That also have a variation of these kind of R kind of things. So in that case, we have to think about where we have to define the actual these kind of a line, even if we have these kind of very rough surfaces. That's the kind of a problem we have to do. And then we usually say about the just kind of a sea level, like average sea level, can be defined about these kind of a smooth surface as an origin. And then based on that, we can actually, assuming that there is a kind of a point going to be representing. But the problem is, like I said, our surfaces are not the kind of have a lot of these kind of elevation variations. So to reflect the very exact point of the locations, in that cases, we have to thinking about the reference system only fit for that specific area. That is what is called the projected coordinate system, CRS. Okay. So for example, like in the US, maybe assuming that this one is the location of the maybe Georgia or Florida as an example. Georgia and Florida has their own topological kind of a condition. Maybe I would say about not this one, maybe Colorado, because Colorado is a kind of a very high, like a Rocky Mountain kind of area in here, like when we thinking about the Denver. So in that case, we need to figure out to represent the exact location of each point near to these area. We have to define the unique coordinate reference coordinate system that only fits about this specific area. That's what the projected coordinate reference system is about. So in case of the Denver, that is actually state plane, Colorado, maybe center, I guess. I'm not sure that is a center or not, but I think that this kind of way of the coordinate system gonna be needed to reflect these kind of a topological kind of a situations, and then try to just find its own coordinate system that represents the exact location of the dead points. So, but the thing is, when we using this kind of a projected coordinate reference system, we cannot use this one for the maybe to represent the location of the Georgia, or maybe New York, or maybe Massachusetts, etc. Because it's a totally different kind of a topological or geometric situation in case of the Massachusetts or New York compared to the Colorado. So that means we also need to use their unique coordinate reference projected coordinate system that fits the exact, that represents, allows us to represent the exact location point within those kind of states. Okay, that's how projected coordinate system is about. And then that's the kind of a coordinate reference system is defined and managed. And then the 2.4 is a kind of about how we can actually express the projections in R, especially in R in here. Because in R, actually, these are the kind of example about the representing these kind of units in here. And also there is some kind of a brief history mentioned. This book actually briefly mentioned about the history about how the projection system is developed. Because early 2000 is projection is the known and projection 4. Because in R, actually, like SP objects, there is a function for project for string function to transform or define the projection of some shapefile. Because these 4 actually come from the like a version number of the projection kind of a definition system. But right now, actually, when you're looking down here, it says about the now it's the version. Its version is like a 5, 6, 7, 8, 9. Is a kind of a version upgrading kind of things, like improving some definition of the coordinate system. So now we just try to call the projection like a PROJ as a whole, like no matter what about the version. But in R, actually, when we have a SP object, not the SF, SP object, there is a function called project for string functions that allows us to define the projection and also maybe projection, those kind of stuff. Any questions so far? Anything? Okay, and then as you can see here, when we looking at these 2 plus, depending on about how we can use the datum and then units as a reference system, we can see that there is a kind of a different kind of a line of the curve that actually represents about the points, locations. This one is a more like a little bit curvy sloped line, and then the figure on the left, right is a kind of north and south. So figure on the left is a kind of like a west and east kind of a line locations to represent the points. And this one is actually mainly axis is a kind of a north and south, kind of a reference points, points to represent these kind of points. Also depending on the some kind of a tool, maybe when we try to reflect the actual kind of geo topology kind of things, these are the kind of example. Because when you're looking at these gray gradient things, this one actually reflects about the actual kind of a rough surfaces of line. So by using these kind of a rough surfaces line, we can also thinking about the how we can represent each point locations. Okay, so that's the kind of how we understand about the coordinate system. And then the final one in here is there is now is introduced about the well-known text tool, which is the most recent and then standardized for encoding the coordinate reference system in here. Because actually well-known text is just kind of a combination of all of these informations as a text. Because we actually talk about these kind of reference systems, and also latitude and longitude and north and east, northing and easting kind of a location representations and angles. So all of these information is integrated into that is a well-known text. And then this one can be used as a kind of fundamental, maybe basic property of the way to representing the locations. So in this one, in this case, is the WPSC 4326 is the WGS 84. And then when we try to looking at the WKT, like a well-known text profile, this is the example of the WGS 84. And then what's the ensemble means about how this coordinate system, about some brief history about how this coordinate system has been developed so far. And then ellipsoid is a kind of like a way to representing the points. And then there is also kind of a ellipsoidal kind of things, and then the definition of the axis, like a geodetic latitude and north, and then geodetic longitude and then east. So north and east, these are the all positive kind of a location representation. And then this one is the negative, and this one is the positive, negative, and negative, negative, and positive, negative. This kind of way is so what I can see here is the north side, north direction, and east direction is the positive value of the latitude and longitude kind of a location point representations. So these all just kind of you can just thinking about these well-known text as far as I know is this one is just kind of combining all of the reference system or datum or this kind of coordinate system is a combination of the information of those things at one single profiling. And then now we can use this kind of a system as it is to represent, to define the projections for our spatial data analysis. Okay. And then maybe I can briefly show you about the this one. Everyone can see this these screenshots. I can share the link in here too, in the chatting. So this one is actually about explain about what is the well-known text format is about. And then here, as you can see, there is an axis, and then datum going to be defined. And then and then the GeoCCS is a kind of a three-dimensional coordinate systems, right? Because center of the with the origin of the center of the Earth, and then the GCS is the based on the latitude and longitude, and then every kind of a property attribute within that well-known text is explained that link. So maybe if you have time, you just feel free to check out about how this format gonna be extended. And also the other thing that I wanted to share is at the end of that chapter, it also explains about the EPSG as a code. So there is also a website called EPSG. I think everyone knows this website. So maybe when you when you enter the name of the coordinate system or country, something like that, maybe if I can type about the Korea where I come from, maybe there might be a lot of a coordinate system can be used, or maybe you can find whatever you want, and also you can transform your coordinates between depending on what's the input and output coordinate system, and then you can also find out when you see here, maybe you can see about the Korean 2000 unified CS is the EPSCG number is 5179, for example. Okay, or with the transformation of the 15831, this number also can be used in R. So the thing is, when you go to this website, you can find about the EPSG number, and then when you try to project your shapefile in R, you can using this kind of a code number as to define the projections. Okay. Or maybe if you have this well-known text file, you can import this WKT file as a references, and then you can define your shapefile in based on this WKT text file profiling informations. Okay, so this is it actually. So I just to try to briefly summarize what chapter 2 is about. So as far as I know, there is some of the other information, a little bit in-depth information about the coordinate system. But the thing is, basically, this is what I think is we need to understand. Just kind of a matter of how we can define the fixed origin to represent a point, and then how we can represent that point by using the distance or angle. So those kind of a combination actually defines about the coordinate reference system. And then depending on maybe some geographic or topology kind of situations, we can also using some of the projected coordinate system just only fit for that specific location point. I think that's all we have. Like in case of the WGS84, that is more like a standardized kind of approaches because we only using that ellipsoid kind of Earth surface without considering any kind of a rough Earth surface, I mean. So that's the kind of how we can understand about the coordinate system as far as I know. So that's I just try to my best to explain this chapter. So is there any questions so far or anything that you wanna add in? Do I explain clearly and then everyone understand what I mean? Does that make sense to you all?
Yes, Kim, thank you very much, because I was reading the chapter yesterday, and well, this is my first time like looking at a spatial data. So I didn't understand some things about the datum in like the coordinate system, but
Mhm.
with your explanation, I think it's a lot clearer now. So thank you.
Okay, thank you. So you just, because again, in summary, you just keep in mind is just about when you're looking at the coordinate system file, I personally think that there is a three things you have to look at. First one is where is the origin, how they define the origin. The other one is what kind of a measurement units they use to representing the point location. And third one is what's there's what I call the location space is about, like they assume the Earth surface is the just kind of a very smooth ellipsoid surface without any topological considerations, or they consider that coordinate system consider that rough Earth surfaces or not. If they consider what the rough surfaces to represent some location point, that coordinate system tends to be very projective coordinate reference system, which means that coordinate system only fits into that specific area, that specific spatial scope of the area. So that means that coordinate system may not apply when you represent the points to the other area. Like a Colorado coordinate system cannot be used to the representing the point location to the Massachusetts, or maybe New York, or maybe UK, or maybe Korea. It is you can transform you can define the projection by using that state plane coordinate system, but the thing is that location that the way of the representing that point gonna be more likely to be inaccurate if you using that stated projective plane coordinate system. Maybe if you can use the coordinate system like a WGS 84 to represent the point, that might be okay. There still might be some kind of a inaccuracy issue gonna be here, within the dead location point, representing of the dead location point. But the thing is, WGS 84 is the kind of like a very standardized location, representing the way of the representing point, just kind of based on the assumption that Earth surface is very smooth and flat, like an ellipsoid, kind of a circle. So those things is just kind of what you're looking at when you try to do the coordinate reference system. So that's the just chapter 2 is about. So I think that this is it for today. And then maybe do you have maybe is there any volunteer to do the chapter 3? Anyone wants to do the chapter 3? Because let me see. The chapter 3 is about the geometry things. So maybe if there is any volunteer to do chapter 3, then
I think I can volunteer for next week.
okay, yeah,
Yeah.
just write your name onto the desk spreadsheet, and then you can feel free to do the chapter 3 then.
Okay, I'll do that.
Okay, so this is it, and then thank you very much, and then I will see you next week then.
Thank you, Kim. Bye.
Yep, bye bye.